Morning to you all. Just a few minutes.
Yes, let's just wait maybe 2-3 minutes just before starting. Yeah. Good
Okay.
morning, everybody.
Bom dia, pessoal. Tudo bem? Saudações.
Bom dia.
Bom dia.
Bom dia, professores.
Olá, pessoal. Bom dia.
Bom dia, professor.
Good morning, ladies and gentlemen. Thank you. The graduate program in physics of the Federal University of Amazonas is happy to announce the opening of the 4th International Conference on Molecules, Polymers, and Material Physics, MP2. This event connects the local scientific community with the current high-level scientific research in materials and molecular physics, both from a theoretical and experimental point of view. We hope to enhance connections between researchers, laboratories, and leading research centers in Brazil and worldwide. We aspire to bring young researchers, undergraduate and graduate students, including senior researchers, thereby contributing to a new and better qualifications of the professionals in the undergraduate and graduate programs at UFAM. For our opening season, we will have a short presentation of the opening ceremony of this event. First of all, let me invite Professor Túlio Orleans Gadelha Costa, Director of the Institute of Exact Science of the Federal University of Amazonas. Please, Professor Túlio, you have the word.
Bom dia a todos, bom dia a nossos alunos de graduação, de pós-graduação, bom dia aos nossos convidados do Brasil, do exterior, bom dia à comissão organizadora e a todos que estão nos assistindo aí pelos meios de mídias aí existentes, né? O Instituto de Ciências Exatas da Universidade Federal do Amazonas se sente muito honrado em receber e sediar essa 4ª edição da Conferência Internacional sobre Moléculas, Polímeros e Física de Materiais, a famosa MP2 2021. Então, é um evento que vai acontecer agora nos dias 18 e 19 de novembro, né? E nesta versão conta com 100% remoto, né? Que a gente sabe que a gente passou por uma pandemia, onde nós tivemos a morte de mais quase 5 milhões de pessoas pelo mundo, né? Então, a gente lamenta muito essa situação, né? A gente gostaria que os nossos visitantes tivessem a oportunidade de conhecer nosso estado, né? Que é um estado fabuloso, um estado grandioso, né? Nós temos aí a nossa maior floresta tropical, nosso maior rio do mundo. Então, material de estudo aqui não falta, né? Então, a gente lamenta, mas torce muito pelo sucesso do evento. Então, como é de conhecimento de todos, né? Esse evento já coordenado pela UFAM, pelo Departamento de Física, pela pós-graduação, pelo programa de pós-graduação, né? Ele começou em 2019, como já foi dito, né? Então, já veio para ficar, né? Então, a gente já espera que ano que vem, né, no intervalo de 2 anos, a gente já tenha o próximo encontro, né? A próxima conferência, né? Então, e o objetivo é aproximar esses alunos, né? Que eu entendi muito bem, nossos alunos de pós-graduação e, consequentemente, nossos alunos de graduação, que serão nossos futuros alunos de pós-graduação, né? Que a gente espera muito que nossos alunos continuem, né, na nossa instituição, né? E a riqueza que é o evento, né? Então, a gente está aí, a gente espera muito que nossos alunos aproveitem da melhor forma, que nós vamos ter, durante esse período, vários minicursos, conferências. Então, sem dúvida, será um momento bastante proveitoso, né, para eles, né? Espero que eles tenham essa vontade, né? Que a gente sabe que que há um tempo atrás era muito difícil fazer eventos dessa natureza, a gente tinha grandes dificuldades, né? E então é para vocês, alunos de pós-graduação, de graduação, esse esforço todo dessa comissão, e a qual eu quero parabenizar aqui e até nomeá-los aqui, a comissão, professor Edgar Aparecido Sanches, nosso pesquisador, professor Puspitlato Chauvin, professor Fidel Guerreiro e a professora Ansula. Recentemente foram professores agraciados com prêmios, estão entre os melhores pesquisadores da América Latina, então agradeço a oportunidade também de parabenizá-los novamente com esse título. Então, é isso que eu falo da riqueza, do grande arsenal de professores, pesquisadores que o ICE possui, né? Isso falam ICE e a Universidade Federal do Amazonas. Então, parabenizo também aos professores, novamente agradeço os convidados, a presença, a colaboração, né? E parabenizo também a comissão, o comitê científico, todos que, de uma forma ou de outra, colaboraram para esse evento. Então, muito obrigado, e eu quero enfatizar mais aos nossos alunos de pós-graduação e graduação, que serão nossos, que eu sempre enfatizo, serão nossos futuros alunos. Aproveitem, né? Nós vamos ter 2 dias de troca de experiência, de possibilidades, né? Então, por isso que a gente só tem a agradecer. E a universidade, mais uma vez, o Instituto de Ciências Exatas se sente honrado em sediar esse referido evento. Então, muito obrigado e bom trabalho a todos.
Thank you, Professor Tulio. Now, let me invite Professor Ansula Ghosh, coordinator of the graduate program in physics of the Federal University of Amazonas. Please, Professor Ansula.
Thank you, Camila. It's a great honor to be here. So, hello, everybody. It's a rainy morning in Manaus. Well, I don't know if everyone is from Manaus, so a very good morning. Welcome you all. I hope you and your family are safe and in good health. It's a great honor to receive you all at our university, though at this moment through just an online platform. Hope to receive you, especially Dr. Simons, you here in future, which would allow you to feel the beauty of this Amazon rainforest and enjoy the beautiful culture and food from Brazil, and more especially from the north of Brazil. We are at north of Brazil. So it's an honor and privilege to participate in the 4th edition of MP2, an international conference on molecules, polymers, and material physics. I would thank the organizers, Dr. Sanchez, Dr. Chaudhary, and Dr. Zayas in making it possible. It's really a big deal now during the COVID-19 situations. My thanks also goes to Dr. Gadelia, our Director of Institute of Exact Sciences, not only for your presence, Dr. Gadelia, but also for your support. Thank you, Dr. Selma. She could not be present at the opening ceremony, the Pro-Rector of University Federal of Amazonas, and her group for the unconditional support. Thanks to the head of the department, Dr. Bittencourt. It has been difficult for all of us during the last 2 years, but I'm really happy to see it happening. During today and tomorrow, we'll be able to experience some very good moments with some wonderful talks from people around the globe. Thank you, our speakers. You have promptly accepted our invitation and made it possible. Our physics program at UFAM involves researchers in materials, condensed matter, and atomic and molecular physics, working both from the theoretical and experimental point of view. So it is just wonderful to be here. I hope all of you, including my students from the program of the graduate program in physics, enjoy these 2 days of academic talks, discussions, and much more. Thank you, everybody. Wish all of you 2 days of sheer enjoyment. Thank you, Camila.
Thank you, Professor Ansula. And last but not least, let's hear from Professor Edgar Aparecido Sanchez, coordinator of this event. Professor, your mic is off. Yes, now we can hear you.
Thank you, Camila. Dear colleagues, professors, lecturers, researchers, ladies and gentlemen, on behalf of the organizing committee, I would like to express my sincere gratitude and welcome you to the fourth edition of the International Conference on Molecular Polymers and Material Physics. It's my hope that the fourth edition of MP2 will be able to achieve its objective in providing an effective forum for students, professors, and researchers to advance in knowledge, research, and technology. In order to put things in context, let me give you a brief description of this event. MP2 is a small conference that's been organizing successfully since 2014 on a biennial basis at the University Federal of Amazonas, located in the city of Manaus, Brazil. The city of Manaus is situated right in the heart of the Amazon rainforest and a little bit isolated geographically from the mainland Brazil. As a consequence, the students do not have frequent opportunities to go out of their city to participate in conference, and the maintenance of a graduate program is a costly affair. So, the main object behind the creation of this conference was to stimulate local students, professors, and researchers, providing them the opportunity to listen to well-known scientists from different parts of Brazil and abroad, and also interact with them without the necessity of going out of Manaus. Although it's called as conference, the true nature of this event is that of a workshop, where the local science community get the opportunity to learn about the state of the art of recent research, advances in different branches of material physics. Given the current coronavirus situation and travel restrictions, we have decided to organize it totally online this year. I would like to thank all of you that are participating in this conference, the members of the organizing committee for the continued support and cooperation during the preparation, the invited speakers, Brazilian and foreign ones, and everybody who worked for this event. I wish you every success to the conference, and I hope you'll be given the opportunity to enjoy the high-level scientific research lectures and to find out as much as possible during the conference about the progress in materials and molecular science areas. May science flourish and grow. May this conference be a complete success. Thank you all. And let me invite again our director, Professor Túlio Gadelha, for the final speech.
I declare open on 40th edition of the International Conference in Molecular Polymers in Physics and Material, NP2 2021. Good job, everyone. Está aberta a quarta Conferência Internacional de Polímeros e Materiais. Bom trabalho a todos.
Thank you all. Please, Professor Ansula, you have the words.
Thank you, Camila. So, Dr. Hugh Simons, so we will just be starting with your talk. The talk, as you know, will be, you can choose, we have 1 hour and 30 minutes. So I'll just give a short presentation. Before I think starting, I would like to tell you that we are a small program of professors doing physics in the heart of Amazon, and it's a great honor to have you here. So let's invite our speaker. So Dr. Hugh Simons is our first speaker of the day. Dr. Hugh Simons is an associate professor in the Department of Physics at the Technical University of Denmark. In the Nanomaterials and Devices group, his work mainly involves studies on ceramics, alloys, utilizing X-ray microscopy techniques. Thank you very much, Dr. Simons, for accepting our invitation. So I would now invite Dr. Simons to start his presentation on dark field X-ray microscopy from multiscale materials characterization. So Dr. Simons, you are the word. If anything I missed out, telling about your research, please help us know you better. And you will have the time now to start your presentation.
Beautiful. Thank you very much. And thank you very much for inviting me. It's really a joy to actually come here and talk about science.
Yes.
So, I mean, I guess like a lot of you, I haven't really had the opportunity to give any scientific presentations for something like 2 years. This is both good and bad. It's good because it's really nice to do this. This is what I really live for. It's bad because I'm hopelessly out of practice. So I'll try and do the best I very can to give give a good description of some of the work we've been doing and to try to make it interesting. It's also really great to be sort of giving this virtual talk to Brazil. Brazil is somewhere I've always wanted to visit. And I can hear the birds outside your windows. And
True.
I grew up in Sydney, Australia, where I'm also used to hearing all these birds around me. So it really it takes me back to where I'm from, which is also a place I haven't seen for many years now, thanks to the pandemic. So thank you also for that. So okay, let's talk about the science, I think. So what I want to talk about today is actually really about a technique we've been developing. So that's me and my colleagues and my collaborators at DTU and elsewhere. And it's a technique for characterizing materials. I think it's really, really important that we continue to strive to develop better ways to visualize what's happening inside materials, not just in great detail, but also in conditions that are truly realistic that the materials operate in. I think that's really essential, both in terms of in understanding things from a fundamental level, but also validating the models that theoreticians make. So a lot of the work I'll be presenting today is been carried out by members of my group at DTU, which I have to say includes Leonardo, who is from Amazonas, him and his wife. So I've heard many, many great things about your beautiful campus in the forest, and he's given me lots of examples of Brazilian food to try, in particular northern Brazilian food. So I wouldn't call myself an expert, but I am certainly appreciative. And in addition, we also collaborate with many people, both within DTU and also at, in particular, the European synchrotron and material science collaborators in Darmstadt, UNSW in Australia, Stanford, and EPFL. And of course, there's many others on this list. I mean, I think if I listed all the names of the people who had helped immeasurably with this work, it would be well over one slide. In fact, it would probably take up the rest of the presentation time. So let's just leave it at this for the moment. So I just want to start by talking a little bit about how we do material science today. Maybe this seems a little bit broad, but I think it's worth considering. If you think about it, actually, particularly those of you who are, actively involved in producing samples, at least as I was during my PhD some years ago, the process is basically you decide which sort of structure and chemistry you'd like to make. You mix the components together, and you in my case, because I do ceramic science, you put it in an oven and sinter it, and then you measure it, and then you see how well it performs, and then you adjust the structure and the chemistry, and you go on and go, and so on and so forth. This is essentially the process of trial and error, and it's with this that you end up with some, optimized material or some optimized component that you're trying to build, whether it be a battery or a new transistor or a new type of polymer or what have you. But the point I'm trying to make is that this process is continually going around and around like this, and because of this, it's quite time consuming, and things that are time consuming are also very expensive. And so I think where the future of material science is going is in fact very good news for the theorists in your department. It's the concept that perhaps we can replace all of these grad students mixing powders together and processing them with simply a computer. So the idea is, if you can have a computer model of a material that is sophisticated enough to take into account the chemistry, to take into account the structure across the various length scales, to take into account the application cases and the kinetics and the processes that take place during processing, then perhaps you can carry out this optimization completely inside a computer. You could do it much faster. And then you would just simply find out what the ideal material is, you would make it, and then you would have it. This is, of course, an ideal future and one that doesn't yet exist, but I still think it's something that's worth dreaming towards. And this is kind of generally characterized in something called the Materials Genome Initiative, which is exactly, a sort of a white paper about how do we get to this stage where we can, fully automate the materials engineering process. So what's stopping us from doing this right now? Well, I guess this isn't news for a lot of you, but materials are in fact very, very complicated. That's a beautiful thing for us as researchers because it gives us something to do, but it's also immensely frustrating if you're trying to actually produce something that the world needs. I mean, right now, the world needs, better batteries for the hugely increasing number of electric cars and other components that we use. And if you take something like a battery, which is really a classic example of a very important material today, you can see it's made up of so many different parts. I mean, in particular, the structures of the anode, which can be, I guess, lithium or silicon, they have these different parts in them, these different grains. As they become used, they get damaged by this lithiation process. This is characterized by individual dislocations. And then locally around that scale, this even has some local atomic disorder associated with it. And the problem is that it's all these different processes which contribute to the overall functionality of something, something you might take for granted every day, such as a battery. And the problem is that this is a big issue for those that are trying to build models of this type of component. So for example, if you want to really accurately if you really want to accurately model the failure process of something like a battery, you need to take into account all of these various effects from the atomic scale right up to the macroscopic. And this is a huge problem for models, right? Essentially, if you were going to do this really from the ground up, you would need to do it atomistically. And if you, as a back of the envelope calculation, try to count the number of atoms you would have in a square centimeter of something like aluminium, it ends up being a huge number. In fact, just to store the positions of all of those atoms, you would need more hard drive space than there is in the entire world. I think at DTU we have a pretty flexible data policy, but it goes nothing like that. So this is a huge problem, right? So to come up with a sort of a bottom-up model is essentially impossible with the tools we have today. And really the only approach we can do is to have materials models which sort of encapsulate each of these length scales and kind of link them together into this multiscale models. And so multiscale modeling for this reason is a really important field right now. But you can't have really, these multiscale materials, I would say, multiscale models are relevant not just for things like batteries, but in fact, actually all classes of materials from metals to ceramics, which is what particularly interests me. Even naturally occurring minerals and biomaterials as well are also classic examples of multiscale materials. But the problem is that, if you want to sort of build these multiscale models, you also need multiscale methods to kind of characterize them and to validate how these models are going to work. So you need some kind of complementary characterization techniques which can assess the behavior of materials at different length scales. So the first thing is that it has to cover multiple scales. You have to use sort of large samples so you can kind of understand the macroscopic behavior of materials, and you need to be able to zoom between different length scales. And the other thing is to really understand sort of structural interplays between, for example, different grains or different types of defects. You need some way of perceiving the shape of things. So you need to understand the shapes of grains, the curvature of boundaries. These features seem to be, or tend to be incredibly important. So ideally, however we characterize these materials, it should involve some kind of imaging process. We also need to understand the structure. I mean, you need to understand like where the atoms are, where the crystal lattices are, how they're oriented and how they're deformed and strained. And we also ideally need a way to see how all of this is changing when we subject these materials to some kind of driving conditions. So you need to be able to, for example, heat something up, or you need to stress it or apply an electric field. And you need to see how the structure is changing, how the shape is changing, and macroscopically what this is doing. So these kind of 4 ideal requirements are essentially what we need for a multiscale characterization technique. And it's these 4 things that we really need if we want to effectively build the multiscale models, which are, I would argue, are sort of the future of materials, materials modeling and materials prediction. But this is a really big problem. I mean, practically, it's a big problem to create techniques that do this. But what I think personally is a great approach worth thinking about is X-ray diffraction imaging. And this is really what I work on. So we have the opportunity to look at large samples, so bulk samples, using hard X-rays. So this is X-rays with an energy above 15 keV. And if we do this using imaging, then we have the ability to map things like the shape of objects inside samples. So, for example, grains. And if we use the diffraction contrast, which I'll go into a little bit later, we can also visualize, for example, the stress and the orientation and the crystal symmetry at a local scale. And if you can do all of this together, you really have kind of a new approach to understand materials at all of these different length scales with the kind of the fidelity that you need to directly validate many of the materials models that are being developed today using, for example, finite element and phase field and DFT type techniques. So taking this example of a battery as a case, we have a few different techniques at our disposal already. So obviously at the very large scale, you can use, for example, X-ray CT imaging. This works quite well, and this has been done for years. But the challenge starts to get when you get smaller than this and when you need some kind of contrast to the structure. And at this kind of micron scale, so particularly in the order of tens to hundreds of microns, there's a suite of techniques called 3D XRD, 3D X-ray diffraction, or diffraction contrast tomography, which give the ability to map not only the position and shape, but also the orientation and strains of individual grains inside polycrystals. The limitation of this particular approach, however, is that the grains tend to have to be sort of 10 to 20 to ideally 50 microns in size, which is okay in some cases, but for many materials, for example, I work in ceramics, the grains tend to be much smaller than this. And so we need to use smaller techniques also, particularly if you want to look at for example, the scale of individual defects. And in the last few years, there's been a lot of progress in something called Bragg coherent diffraction imaging. And these are essentially a suite of techniques which utilize the coherent nature of very, very perfect X-ray beams, usually generated using synchrotrons or X-ray lasers. And these give you very, very high resolution and also contrast to strain and misorientation. And the resolution is today something close to, I think, 15 to 20 nanometers. So it's very good. But the problem is that these types of techniques, the field of view you can have is very small. In fact, they're really mainly limited to, for example, either very thin films or essentially nanoparticles, so things smaller than a micron. So the problem is that you have techniques which can visualize things which are essentially larger than 5 or 10 microns, and techniques which can visualize things that are smaller than 1 micron, but actually not really much in between. And this is a really big problem, because if you want to build kind of a continuous pipeline of techniques that can visualize structures and their dynamics across multiple length scales, you have this big hole in the middle, which is exactly where you need something. And so this is essentially what I'm talking about today. So it's a technique we've developed at DTU in collaboration with the European Synchrotron, which we call dark field X-ray microscopy. And the whole purpose of dark field X-ray microscopy is essentially just to bridge these length scales between Bragg coherent diffraction imaging and DCT/3D XRD. The beauty of giving an online talk is I can have a glass of water next to me. I hope you don't mind. So this is a technique we've been working on for some time, and it really, I would say, came to fruition about 2 or 3 years ago when we built this instrument shown here. So at the European Synchrotron, which is one of the largest and most powerful synchrotrons in the world. In fact, I think at the moment it is the brightest synchrotron in the world.
Dr. Simons, I just have a question.
Yes.
Will you be sharing your screen? Will you be sharing your presentation?
You can see my screen, can't you?
I can't. We can't.
Oh my
No,
goodness.
we can't.
Oh my goodness. Oh my goodness. Oh, you've missed all my beautiful slides. Thank you
Oh
so
my
much for
Not a
bringing this
problem.
up.
We
This
still
could have-
have time.
The
Yes.
problem
We
is that
can
if you give
scroll
a
through it.
if you give a talk about imaging, it doesn't help to not show images. So
I was just wondering if you're just doing a for talk, not a problem.
Yes, I just thought so. We were just
Wow,
waiting,
okay.
and so
I'm so sorry.
no, it's not a problem.
Can you see this now?
Let me see. Yes, now it is
Yes.
presenting. Yes.
My goodness. Okay.
Thank you.
Then you'll see
If
what I
you
was
just
talking about
can
when I was
maybe,
talking about my group.
yeah, just go fastly through what you wanted to say and just.
Okay. Oh my goodness. Now you know I'm out of practice. Okay. So this is the current sort of process of materials development, including this kind of trial and error approach. The whole idea is to replace this by a computer. This is my example of a battery where you have the different length scales which are relevant. And the fact that these are relevant, in fact, across pretty much all materials. I think batteries are a nice example, but metals, ceramics, minerals, and in particular biomaterials, they all share these same like multiscale hierarchical structures. These are kind of my wish list of what you need if you want to be able to characterize these multiscale structures. So you need all of these rolled into one. And I was saying that my solution for this is essentially X-ray diffraction imaging, which we think is a good way to combine being able to both visualize things spatially, but also to map quantitatively things like stress and orientation and lattice symmetry. Now we're almost up to date. So I was saying that at the various length scales, particularly at the coarser length scales, we have, for example, DCT and 3D XRD. And at the smaller length scales, we have Bragg CDI, but we don't really have anything in between. And this is what we're trying to address with dark field microscopy. And now we're up to this slide. I'm so sorry about this. So this instrument here, you can see, actually, I really do sincerely hope you can see this time. So this is essentially this dark field X-ray microscope, which as far as I can tell, I think must be one of the largest microscopes in the world of any kind. So it's installed at the European Synchrotron, which is in Grenoble in France. I think the whole instrument itself weighs in excess of 20 tons, I think. It's 6 meters long, and it was finished about 2 years ago. And actually, since installing it, this has now been sort of branded as one of the flagship beamlines in the ESRF upgrade. So in the last 1 to 3 years, ESRF has been upgrading. It's been changing the entire source effectively to become a so-called diffraction limited source. So I'll go into a little bit of detail about this later. But it essentially means that it has the brightest photons of almost anywhere in the world. And as part of this upgrade, they were looking to support new techniques which utilize this behavior. And this dark field microscopy is a good candidate for this because it's very, very photon hungry. But as I'll show, you use a lot of photons, but you can truly do some remarkable things with them. And so the way dark field microscopy works is this, and this is where it's really, really essential that you can see my screen. So the idea is that generally we start with some bulk sample. So the sample can be kind of millimeters in size, and it can be a single crystal, it can be a film, or in this case, it's a polycrystal. So you imagine a polycrystal, for example, with many crystalline grains in it. And what we do is we use a series of optics to illuminate the entire sample using a very intense beam of hard X-rays. And then within our sample, we position our sample such that one particular, I should start by explaining how a conventional microscope works, an X-ray microscope. So in a conventional X-ray microscope, you would have contrast due to the absorption of the various components inside the sample. And then you would use, for example, an X-ray lens, an objective lens, to magnify that and create an image on a detector. So we call this bright field imaging. But if you want to see just one type of structure inside this, say, for example, this pink grain, what we can do is we can move this entire imaging configuration into the path of the diffracted X-rays. So this is what we call dark field X-ray imaging. So this is exactly analogous to dark field and bright field transmission electron microscopy. So in dark field X-ray microscopy, essentially we're creating a magnified image of a single buried structure inside a material, where the contrast is given by the diffraction process. So in other words, it gives us a real space image from a finite volume in reciprocal space. And this gives us like image contrast, so intensity contrast, due to the tilt of the lattice inside this grain, and also the lattice spacing along a given HKL. And so this essentially gives us lattice strain. So we can map, for example, tilt and strain by recording many, many different images at changing, for example, the sample tilt across these sort of two orthogonal angles, or also changing the 2 theta angle of this, this microscope, essentially. Then when we have like a stack of images at different rotations, we essentially take the position where the intensity of any pixel is the maximum, and this corresponds to the true orientation or strain of that lattice. And right now we have a spatial resolution of something like 70 nanometers at between 17 and 35 keV. And we have an angular resolution of about 0.001 degrees. This all depends on optics, but it's I would say our spatial resolution is good enough to see many small features, but our angular resolution is really quite exceptional. So in many cases, it's in excess of, for example, what you can get with TEM. And so this allows us to see sort of very subtle deformations inside materials, which, as I'll hopefully show later on, are quite important for the material properties. So as we sort of make a scan, we end up sort of scanning through orientation space and kind of progressively building up an image of how, for example, a buried grain looks in terms of orientation. So this is essentially a grain of aluminium where the subgrains are given by different colors. So you can see we have some orientation variation inside our grain, and we slowly build up this picture up as we scan through orientation space effectively. So that's pretty much how the technique works. I now want to give some examples of how this, exactly the kind of work that we've been doing, starting with just some work in aluminium. This is really, sorry, this is where we began our experiments. Aluminium is a nice model system for us because it's easy to get and it scatters properly. So aluminium is also a classically multiscale structure. In particular, as many of you know, the aluminium you have in cars and fry pans and things is polycrystalline. So you have many of these different grains, and but inside these grains you have what are called subgrains. So you essentially have regions of perfect crystallinity separated by these lines of dislocations effectively. And these give very sort of small but discrete orientation differences between the different subgrains. And the way that these subgrains interact with each other is very important for crystallization. So there's effectively 3 methods for recrystallization as aluminium. The first is essentially subgrain coarsening, so where these subgrains get larger and sort of eat each other, for lack of a better expression. There's the nucleation of new grains, for example, where new grains will form and grow at the expense of others. And then there's classical grain growth as well. And one of the real questions is to what extent do these 3 processes take place under different conditions in recrystallization? It's tremendously fundamental to how we use and process something like aluminium, but it's also something which is really, there's no clear consensus on today. So this is kind of a nice candidate material for dark field microscopy because the orientation resolution allows us to see these subgrain structures. So this was done by a PhD student in our group, Sonia. And before she did any kind of microscopy, she started by looking at just the diffraction spots from individual subgrains. And so this is what you can see as part of a diffraction ring, and these spots are essentially individual subgrains. And she watched them as the material started to heat up, and you can start to see that these subgrains start to get larger and larger and larger. So it kind of looks like a bit like Christmas lights, actually. And the beautiful thing is by sort of analyzing what the intensities are and the number of these subgrains just in these images, we can use just computer programs to try and make some statistics on them. And by correlating because we know that the volume of the grains are related to their brightness, you can sort of estimate what their radius should be. And so as the sample was heated, Sonia was able to make these statistics of tracking exactly what's happening to the individual subgrains. And although this doesn't use microscopy, this gave us really some insightful information, because it shows that there's really no clear correlation actually between the initial radius of the subgrains and actually how fast they grow and to what extent they grow. And this really sort of flies in the face of conventional wisdom in terms of recrystallization. And this is what made us really motivated to try and use the microscope to actually understand why this is the case. And so this is what we did. So what you can see here on the left is an image of the lattice orientation. And on the right, you can see essentially the uncertainty in this misorientation. So this corresponds to where the boundaries should be. And what you can see is there are basically some subgrains. So you have different regions that have different sort of average misorientation, and you see some clear boundaries between them. And what actually we learned from this is that if you look very carefully, you can see the boundaries between the subgrains are associated with some kind of retrusions, so some indentations effectively in the sides of the grains. And this essentially corresponds to the grain growth being inhibited by the intersection of the grains with these subgrain boundaries. So essentially what's happening is the grain boundaries and the subgrain boundaries are pinning themselves, and they're preventing further growth. And so this turns out to be exactly the mechanism that we're absorbing for this this unusual and unpredictable subgrain growth within these materials. But looking at these subgrain boundaries got us thinking. We know that these subgrain boundaries are characterized by lines of dislocations, and we know that dislocations are kind of one of these fundamental building blocks for understanding material deformation and behavior. So is there a way we could kind of look at these in a bit more detail? And in fact, this is another example of Sonia's work, which showed, I think, a line sort of much more clearly. So you can see these lines here and these sharp changes in intensity. These are essentially from very, very low angle grain boundary lines, which are almost single dislocations. In fact, I think the circled area above is a single dislocation. And so we got to thinking, if we found the right sample and we improved the resolution a little bit, is it possible that we could see kind of individual dislocations buried deep inside like millimeter samples? And that's the size of the samples we're working with here, is they're about 1 millimeter thick. So before we looked into aluminium, we thought, okay, let's see if we can find a simpler model system. And so I was talking to some people from my old university who said that, if you want a sample that has very, very few dislocations in, you should take my thin film of bismuth ferrite, because they said this is a near perfect film, there should be no defects in it. And so I put it in our microscope, and we saw all of this strain and misorientation all over the thin film, and it was very clear that this, in fact, wasn't a perfect film, but not just that, but actually we're very sensitive to these small misorientations. And actually, what we saw were these changes in strain and these changes in misorientation. And although we were kind of looking for dislocations, it wasn't so obvious to me how or why these were dislocations. But I got talking to some of the people that work in solid mechanics in our university, and they gave some advice about how to analyze these in terms of essentially the dislocation density tensor. And it turns out that when you measure across certain misorientation changes across certain directions and also different strain components, you can actually isolate very specific components of this dislocation density tensor. And because of the particular HKL we chose when visualizing these samples, these actually corresponded to very relevant coefficients. So in this system, which is bismuth ferrite grown on dysprosium scandate, you should in principle have misfit dislocations, and these should move along particular lattice directions. And in this case, these two panels corresponded to the density of edge dislocations, and then the lower panel corresponds to the density of screw dislocations. And in particular, if you look at the lower panels, you'll see you have blue dots and you have red dots. And in fact, if you integrate sort of the density around one of these blue dots, you get a density of 1. And if you, or negative 1, I should say. And if you integrate around one of these red dots, you get a density of positive 1. And that's because each red dot is an individual dislocation and each blue dot is an individual dislocation. And the sign of them corresponds to their chirality. And so this fits very beautifully, I think, with this image of essentially misfit dislocations in thin films. So what we're actually seeing is we're seeing the the screw dislocation from the surface to the substrate film interface as a screw dislocation as one of these dots. And then we're seeing an edge dislocation propagating between the film and the interface, and then coming out of the sample again as a screw dislocation. And we can show this, I think, quite clearly now. And what's really interesting is because we can visualize the strain and the misorientation, it gives us a chance to see how the lattice is deforming. And because bismuth ferrite is, in principle, an insulator, when you deform an insulator, when you apply a strain gradient to an insulator, you cause something called the flexoelectric effect, which is essentially an induced electric polarization due to the distortion of the lattice. And because we know what the strain gradients are, because we measure them and we also measure the misorientation, we can actually characterize what this flexoelectrically induced polarization should be. And so if you look at this, which is the flexoelectrically induced polarization vector around an individual edge dislocation, you can see that they point to each other in kind of this head-to-head formation. And so this implies that just due to the deformation of the lattice, that in fact these edge dislocations should be reasonably charged, actually. And so from this, you learn that these misfit dislocations actually have, create stray electric fields, and therefore they should have, an electrical impact on the properties of these materials. So we thought this was, pretty interesting from the perspective of dislocations in thin films. But it was only in a thin sample. So soon after that, we started looking for some thicker samples with larger dislocations. And we happened to have this piece of artificial diamond. And using a slightly different sort of experimental configuration, we were able to rotate the sample whilst maintaining in the Bragg condition. And this allowed us to collect data in this so-called topotomography mode, which is kind of it's a lot like a sort of tomographic 3D scan. And so what you can see here are individual dislocation lines inside diamonds as the sample is being rotated through 360 degrees. And by changing the magnification of the X-ray lens, we can see this both kind of as the overall structure throughout the crystal and also in much greater detail. And you can see as you zoom in with some detail, you can start to see sort of finer features in the material, like, for example, this stacking fault in here. So this was, just an interesting case. We thought, okay, maybe we can visualize dislocations in 3D and in bulk materials. Can we do something else? So we got talking to a collaborating group in the University of Darmstadt in Germany, and they were working with strontium titanate. So it seemed a bit crazy to do dislocation studies in ceramics because ceramics are not particularly well known to be plastic. But actually, it turns out that if you orient something like strontium titanate to exactly the right orientation, it can in fact become very plastic to the order of 1 or 2% of deformation, which is almost what you would expect to see in metals, for instance. And they had done some visible light microscopy and seen these dramatic patterns forming due to the dislocations. And they were able to make these kind of notch-type specimens, which created these periodic arrays of edge dislocations. And the idea was that essentially these dislocations, excuse me, should have different electrical conductivity through them compared to the bulk. So the idea was that maybe they can have some kind of tunable electronic properties of their material by maintaining or by perturbing the distance between these dislocations. But the problem is they had really no way to understand what the dislocations were doing, in the bulk of their crystals. So we used this topotomography technique again to visualize the sample, and you can see this is the outside of the sample, and there's kind of deformation around the notch tip just in here. And then if we use our microscope, we can zoom in a little bit further and see how these are positioned in planes. And so to give you a bit more of a description, you can see that you form these individual dislocation bands. And as you change kind of the viewing angle, you can actually see the individual dislocation lines running through the material. And so this data, in fact, allowed us to kind of visualize exactly how these dislocation lines are bending and kinking as they pass through the materials and how they're interacting with one another. And this ultimately gives insight into the mechanism by which they form and the mechanism by which they enhance or affect the conductivity of the material. We're also, able to test different methods of visualizing them. For example, taking slices and moving through the material to visualize how these dislocation bands are sort of distributed through the material, and they sort of create these very dramatic sort of videos of slices essentially moving through the sample. And so here you can see this colorful plots show the lattice misorientation as a result of these dislocation bands. And I think quite clearly here you can also see the deformation in the surface of the material. And I think this is really telling as to why it's important to characterization on bulk materials, right? Because you can see how much the sort of the local structures are different on the inside of the material versus on the surface. I think techniques like SEM and AFM are really wonderful for a lot of reasons, but the problem is that when you want to understand the bulk properties of materials, you can be quite limited by looking at the surfaces alone, and I think this needs to be taken into consideration. At this point, we were getting pretty confident with our abilities to visualize dislocations. And so at this point, we started working with a collaborator now at Stanford. And she was interested in if we could capture really the dynamics of dislocations. And she had a piece of aluminium that she heated very close to the melting temperature. And you can see this is, in fact, the low angle grain boundary consisting of individual dislocations. And you can see as it's heated up, the dislocations start moving around and sort of breathing. And you can see in particular in here cases where they, for example, move together and combine. And we can see, we made a series of these videos actually, and you can see situations where they, for example, self-annihilate and split up and, for example, move towards the edges of the material. So this work was recently published in Science Advances. And if you look in the supplementary information there, you should find a whole host of other videos along these lines. I'd encourage you to check it out. And that's essentially where we're at with the dislocation studies at the moment. Another line of my research involves essentially ferroelectric. So this is a class of materials I'm very passionate about since working on them as a graduate student. And ferroelectrics are interesting. They're functional materials which are really at the heart of, in particular, capacitor materials, but also actuators and sensors, and they have a very large technological role. This is really critical because for something with such a large technological role, we really understand very, very little about them. What we do know, however, is usually gained from the assumptions of structural symmetry. So the properties of the materials we know are very highly linked or very closely related to what their average crystal symmetry is. So, for example, barium titanate, which is one of these classical ferroelectrics, behaves the way that it does because it's tetragonal. And the way we know it's tetragonal is because if we do powder XRD, you have a pattern that looks like this, and this can be perfectly indexed as a tetragonal unit cell. And this is the way that the state of the art has been for the last 50 or even 70 years, actually. That's all well and good. And, I spent my whole PhD basically doing X-ray diffraction studies on barium titanate. So I've completely trusted this. But then one day we were doing some studies of this barium titanate, and we made the mistake, or perhaps the stunning realization of looking, in fact, at the individual diffraction spot created by not just a powder diffraction scan, which is a sum of all the different grains in the sample, but of just one individual grain. Now, there's an expectation in ferroelectrics that because they're very strongly twinned, that the peaks in the diffraction in the reciprocal space should be very nicely separated. So they should be in this kind of square pattern, which is what we see here. And in general, this is exactly what we see. But the problem is that you also have all this other sort of diffuse intensity in between. And so this diffuse intensity comes from things like strain, it comes from unusual twinning angles, it comes from dislocations. But the problem is that you lose all of this information when you average it together in a powder diffraction pattern. And the problem is that all of these, essentially this misplaced intensity, I would say, this diffuse intensity, corresponds to symmetry breaking. And this is a really big issue because, as I said, our understanding of these materials is based on the underlying assumption that they have a given symmetry, like tetragonal in this example. And if the material is strained, then it breaks that symmetry. So then you have to start questioning your underlying assumptions about why the materials behave the way that they do. And so when we did dark field microscopy on this sample, it's akin to essentially slicing or making a single slice through a single grain very deep inside the bulk. And so with this single grain, we can then visualize, for example, what the strain is. And it's quite beautiful, actually. I mean, you have this ceramic, which can be macroscopically sized. You illuminate it with your X-rays, and then on your detector, you see this beautiful image of just an isolated grain. And this is just one grain of many thousands or millions that are buried inside the sample. It's almost a sort of religious experience. And you see these changes in intensities that come, for example, from the grain boundaries around here, but also the domain boundaries, the domain walls or the twin boundaries that are inside the material. And this is really important because, I mean, ferroelectrics are also one of these classically multiscale materials. You have inside some device like a capacitor here, you'll have grains. Inside those, you'll have these domains of different lattice orientations. And then the structures of the domain walls are also very important. And while there's been previously some studies using this 3D XRD technique to look at the grain structure, there's really not a lot known about what happens at smaller length scales than that inside bulk materials. And this is where we think dark field microscopy could be something really useful. And this is exactly the study we did. So we looked at this one grain and we were able to visualize the lattice orientation due to the different domains and also the lattice strain that's associated with this. And at first thought, I mean, this makes a lot of sense. You have domain walls that fall along sort of 110 type lattice directions. And also these ones, which are also at 110 lattice directions, but it's going at sort of 45 degrees into the screen. And you can also see sort of features you might be interested in. So for example, these domain walls at 45 degrees here, these other domain walls here, and also grain boundaries. But if you look a little bit closer and you start looking at kind of how the lattice orientation and the strain is distributed around these defects. So I'll just show you some zoom-ins of exactly these types of features. You can see something very important here, right? Which is you can see the gradient of the strain extends right the way sort of through here. And this is in the scale of kind of 5 to 10 micrometers. And the same thing happens with domain walls. So the strain fields generated by the domain walls are really extending the full extent of the domains here. And this is a really big issue because these strain gradients then break the lattice symmetry. And because the material is subjected to these strain gradients, it also changes fundamentally the electronic and the functional properties of these materials. And that's what actually all of our current theory is kind of based on, the fact that all of these should be unstrained. And if you look at the sort of the fundamental theory for example, domain walls, for example, DFT in particular sort of states that the size of these domain walls should be very, very small, in the order of a few nanometers. But what we show here is that, in fact, their effects are much, much longer ranging. So, you know, more along the scale of tens of micrometers. And this has a really dramatic impact on the way that, in particular, these domain walls self-organize during electric fields, for example. So in ferroelectrics, when you apply an electric field, you have this very characteristic polarization hysteresis. And this occurs as, for example, the domains reorient and change essentially their volume fraction as the electric field is applied. And the beautiful thing is that because, you know, we have lots of space around the sample when we do these experiments, so we can afford to put electric fields on and track how, for example, the domains reorient. And this is exactly what we did. So as we applied an electric field, you start to see the pink domains get very larger because they correspond to domains which are oriented parallel to the electric field until they form these nice big stripe patterns. And then as we remove the field, you would expect kind of this poled structure to more or less remain where it is. I'm sorry. And that's actually not what we saw. Well, there are some similarities, but the problem is that you form these new kind of like blue colored domains. And more worryingly is you form domain walls at sort of oblique angles. Now, these domain walls should be, if they're sort of classical ferroelectric domain walls, should be at, you know, at 90 degrees or 45 degrees. And this is really not at either of those. And so you end up having domain walls at strange oblique angles. And this is not energetically favorable. And this is a direct consequence of effectively domain wall pinning from grain boundaries. So now we have the opportunity to really sort of track these types of features directly. And I think what's really exciting is we're also able to capture videos of these domains switching as we apply the electric field. So this is effectively in real time. So you can see the intensities changing as the domains go from one orientation type to another. And so now they're disappearing because they're moving into a different orientation, which is outside of the Bragg condition. We're also able to make these kinds of videos on other material systems just out of interest. This shows an electric field-induced phase transition in another ferroelectric called BZT-BCT. So as we apply an electric field and release it, you see the structure change and new domain walls form and disappear. And in a more classic ferroelectric, potassium niobate, you can also see new domains form in this thermally induced phase transition. So if we rewind a little bit, you can see exactly at this point, sort of new domain walls form at oblique angles. And as we heat up, these begin to sort of proliferate through the sample. And this is really nice because this gives us an opportunity to correlate with, for example, in particular phase field models. So in ferroelectrics, one of the leading modeling techniques is a thermodynamic modeling tool called phase field modeling. And this can predict, for example, the strains and the polarization and orientation relationships between neighboring domains. And so by carrying out these types of simulations in the same conditions and comparing the values to our experiment, we really have a nice way to both to validate the models and also to guide us into new ways of engineering these materials. Now, as a last couple of examples, I'm going to list some work done not by me, but by my colleague, Phil Cook. So Phil is very interested in biomineralization. I think this is a really beautiful example of how we can do dark field microscopy. So a great example of a biomineral is bone, actually. So bone is tremendously strong, considering the fact that it's just considering what it's made from, actually. And one of the reasons for that is because this hierarchical structure of essentially these hydroxyapatite crystals held together with collagen. And this is why bones can be so strong. But another incredibly impressive one is nacre. So nacre is effectively what scallop shells are made from. And I only recently learned that, in fact, scallops can swim, which is mildly terrifying, but pretty funny to watch, I have to say. But one of the beautiful things about scallops is, and perhaps not, I mean, I think one of the beautiful things about scallops is they taste good, but another impressive thing is they're actually incredibly strong. If you've tried to break a scallop shell, particularly a fresh one, it's really hard to do, particularly without cutting yourself. And then if you consider the fact that what the shells are actually made from, this nacre crystal is in fact not very intrinsically strong. It's the fact that they're sort of held together by these mineral bridges, and they form these multiscale structures. And this is really the origin of their strength. And so inside these kinds of structures, they tend to form these polycrystalline these prisms. And actually, this is also one of the early tests of dark field microscopy, was that we're able to not just see kind of how these prisms are aligned, but actually even see the internal structure and the strains that happen inside them. And this is kind of very much ongoing work, but I think it's a nice demonstration of the sort of the different ways that we can use this technique, because in effect, this is not limited just to metals or ceramics, right? But it's any crystalline material. In fact, any acrystalline material, anything which has sort of some sort of small or large angle scattering, I think is a nice candidate for imaging using these diffraction imaging techniques. And in fact, something we're very interested in doing down the track is looking at, for example, polymer and glassy materials. So speaking of the future, this is what my last few slides are about. And we have a few ideas. The first is a technique for improving the resolution of our microscope. So if you've read much at all about how microscopes work, you'll know that the resolution is limited by something called the numerical aperture, which is effectively how wide an angle of light can you collect with your lens. So this is why if you buy an SLR camera, for example, the better lenses tend to be much physically larger and much heavier. This is because have to be much larger to have a large numerical aperture to give you a clearer image. And right now, when we build our microscope, we use a lens technology called compound refractive lenses, which are nice because they're easy to make and they're easy to align and they work well. But they have a very, very small numerical aperture. So we spent a lot of time looking for new types of lens technologies which have larger numerical apertures. And one of those is called multi-layer lenses. And essentially, they're a combination between a mirror and a zone plate, which is a bit strange to imagine. But essentially, they're produced via like sputtering and microfabrication processes. And there's only really a few groups in the world that can actually make these things. They're incredibly small. So I think the scale bar here is about 20 micrometers. So they're tiny, tiny lenses, and they have to move very close to the sample. But they can give us, at least the initial tests we've done, gives us resolution of something close to 25 to 50 nanometers, which is 3-4 times as good as what we can currently do. And the latest tests have been getting closer to 5 nanometers. Actually, it's quite incredible. And because they have very few aberrations, and they also allow us to do sort of, for example, coherent imaging techniques such as phase contrast imaging, for example. So this is just, I think, a low intensity contrast testing image that we tested, just test for this phase contrast. Something else we're also working extensively on at the moment is ways to kind of get more out of the information we have. So right now we've just been measuring intensity. But, you know, X-rays are electromagnetic radiation. There's more to them than just intensity. There's the amplitude, but also the phase. And so if you have a way to sort of determine the phase as separately from the amplitude, you also have really another sort of yardstick with which to measure your materials. And so this looks a lot like a microscope made from Lego, and that's because it is. This is a paper published some years ago where essentially a group in the US were able to show that you can carry out this phase and amplitude deconvolution in a regular microscope by illuminating from different angles. And in fact, they were able to build this kind of microscope just using Lego. It was really impressive, actually. But because the classical light microscope is actually very similar in concept to what we're doing with dark field microscopy, we also have the potential to do the same, actually. And so this is something we've been working on a lot in the last few years. And that's to introduce something called Fourier-Bragg tachography. And the idea is that we simply move our objective lens, which is what we need to do anyway in order to measure strain and misorientation. But by using essentially an iterative process, we can reconstruct both the amplitude and the phase. And so with doing this, we essentially merge these techniques like Bragg coherent diffraction imaging, or Bragg tachography as it's often called, and use many of their techniques as well to improve our approaches here. So this sounds very hand-wavy, and I'm sorry it is for the moment, because this is still very much a work in progress for it. But we're very excited because it gives us a method not just to improve the spatial resolution, but also to really separate the amplitude and the phase. So what we've tested so far, we've been able to improve the spatial resolution quite significantly. We've also been able to measure the phase. And this is particularly interesting in our view for ferroelectric materials, because if you have sensitivity to how the phase of the X-rays is changing, you also have some sensitivity to the atomic displacements. And in a ferroelectric, or in fact any like insulating material, the atomic displacements are related to the polarization of the material. And so what we're really hoping down the track, and this is something we're really, really close to finalizing. Although I think I've been saying really close for the last few years, but now I feel we're really, really close to being able to really extract the polarization inside materials in 3D. So this is some measurements we've made of lithium niobate, which is a classic optical ferroelectric. The domains should in principle be invisible from diffraction, but we can get some contrast from the phase jump at the domain boundaries, which are here, and then we can quantify what this phase difference should be. And so right now we're working on correlating this quantification of the phase to the polarization of the material. To do this, it turns out to be not so trivial, and we're essentially building a multiscale model using DFT to try and calculate the correlation between optical phase and atomic displacement. So I'm hoping this should be at least finished in the next few months. And I think the last thing I want to talk about is another sort of cause for great excitement, in particular, not just our technique, but actually all diffraction and all imaging techniques, in fact. And that's because I'm not sure if you guys are aware, or I hope you are, but there's been a huge improvement in the quality of large-scale X-ray facilities in the last couple of years in the form of these so-called ultimate storage rings. So the first one to be built, many of the synchrotrons we know today have been this so-called third generation, but with Max 4 in Lund in Sweden, which conveniently is very close to DTU actually, is the first of these so-called fourth generation sources. And in this case, in conventional sources, the X-rays are often quite spread out, but Max figured out a way to make them very narrow. This makes them much more coherent, and it means using sort of coherent imaging techniques like our tychographic method. It makes them much easier and much more powerful. And so Max got up and running just a couple of years ago. The ESRF shortly upgraded in around this year, basically. And I hope some of you also know that the Brazilian synchrotron Spirit is also one of the world's first fourth generation synchrotron. In fact, I think they were, the second after Max, actually. I'm not sure how developed they are in terms of end stations, but from what I understand, the source is working very well. And it's really a world-class facility. So if you're not going and using it, then I suggest doing what you can to do it, because it's, to have something of this quality in your backyard, although I guess Brazil's backyard is quite a lot larger than Denmark's. But if you have this at your disposal, then you should use it, because it's truly capable of fantastic things. But something we've been doing recently is testing how fast can we do dark field microscopy. And what we thought would have been the ultimate thing would, in fact, to build a dark field microscope at an X-ray free electron laser, which rather than sort of generating X-rays in a ring, generates them using a linear accelerator. And it does so in very fast, short pulses. And these pulses are so short, they're something like tens of femtoseconds. And what we did in our experiment, this is very new data, it's only a month or two old, but we took a single crystal of diamond, and we repeatedly hit the diamond with some light pulses to create a sort of a repeating shock wave, or essentially a single acoustic phonon propagating through the material. And then we're actually able to image this acoustic phonon from the strain fields that they're associated with. And so that's exactly what you're seeing here is as an acoustic phonon being propagated through the material. It splits into longitudinal and transverse components, which have sort of slightly different velocities, which is what you're seeing here. And then you can see they bounce back from the back of the sample to the start again. And this, I think, is super exciting. This in principle means that we can, for me, I've spent my education reading about what phonons do and why phonon scattering is important. But to me, they're always kind of an abstract concept in solid state physics textbooks. But now we actually have the ability to visualize acoustic phonons inside materials almost in real time, actually. So this is just a test case, but we're really excited to be moving forward with this and sort of measuring not just idealized acoustic phonons moving through materials like diamonds, but actually watching how they, for example, interact with defects like dislocations and grain boundaries and domain walls, and how they give rise to phase transitions. So this is something we're working on at the moment, and we're very excited about. And with that, I have that was my final slide. So I have to thank you all for your attention, and if you have any questions, I'd be happy to answer them.
So first, thanks, Dr. Sammons, for the wonderful talk and materials. Thank you, Dr. Sammons. I would just like to ask, first of all, if anybody has a question. I have seen two questions they have put in two of my students have put in the chat, and I can read it for you. I just wanted to ask you a question before going to the questions from the chat. You say that you see the dislocations, and the dislocations are just beautiful, right? So can you tell me, why is it beautiful?
I think I mean, why are dislocations beautiful? I mean, I think part of this is a little
because you know what, when we see imperfections in material, as theoreticians, I'm a theoretician, so we find that maybe it can bring some trouble, but you say they are beautiful. That is my question.
You know, I have a 2-year-old son, and he's both beautiful and trouble. So I think a lot of this has to do with the fact that you read about dislocations in books, and then to see one in front of you sort of dancing, you know, in temperature, I think is quite amazing. But I think it's I think I think particularly from the point of view of a theoretician, it's very beautiful to see dislocations in isolation, because this is something, for example, using DFT. I mean, well, DFT is a little tricky, but as I guess you know, but I mean, you can potentially model individual defects using, you know, atomistic methods. And
I
so
think
the
we can
fact that we
orient
can,
them to do to be useful for some kind of maybe applications.
yeah, so if we can visualize individual dislocations under realistic conditions, I think this is exciting, because it means that we can really validate, you know, these advanced techniques for simulating and modeling them. And for me, that's very exciting.
Another question, I don't know if I just missed out. Maybe you say it's a dark field X-ray microscopy, right? Why is it dark field? I just missed out, maybe.
Okay, so it's borrowing the terminology from 100 years of optical or electron microscopy, basically. So in electron microscopy, if you image using contrast from the transmitted beam, that's called bright field. And if you image using contrast from the scattered beam, this is called dark field.
Okay.
And in electron microscopy, that scattered beam comes from essentially Bragg diffraction, which is the same as what we have here. So we're trying to sort of borrow the naming convention from electron microscopy.
Thank you. Well, I'll just, I can read the questions. First, it was made by Ayersu, who is a student from our program. Ayersu, I will try to read out the question. I don't know if you want to read out. But well, as he writes, good morning. He understands that the X-ray incident which is incident in a sample, and where you can detect these variations in various directions. Is that true, that you make the X-ray beam incident on the sample and you detect the variations in various directions, right?
Yeah, that's exactly correct. That's exactly correct. So you have the X-rays are scattered in slightly different directions, and then we move our lens around to measure them. That's correct, yeah.
And if true, he says, can you tell me that if high pressure can be applied to detect these variations in various directions?
Do you mean like can we do this under high pressure?
Yes, yes.
So yeah, I've never done this. So actually this beamline, this dark field microscopy beamline was just made like publicly available. So if you want to go and use it, you can just apply for beam time and go there, right? But my understanding is some of the external users have tried this with high pressure. So we have something like 20 or 30 centimeters around the sample, which is enough to for example, put in a diamond anvil cell, for instance. So I've never done it, but I've heard it has been done.
It is possible. It should be possible.
It's absolutely possible. Yeah, that was one of the this sort of advertised science cases that we made for it, actually.
So Ayeshu, is that the answer? Are you happy with it? Well, I don't know if he's, yes. Okay, he says yes. Well, the next question is from Emerson. He's also a graduate student. Well, Emerson, do you want to read your question or do you want me to read it?
So was that a question to me or to him? Yeah,
he says, can you use these measurements to help study fossils materials? Can you localize fossil cells or protofeather structures, for example?
So like fossilized
materials?
Like dinosaurs?
Yes, I think so. Is it true, Emerson? You want to know about dinosaurs?
Wow. You know, I never thought of that. What a wonderful idea.
Well, Emerson, you can just try to explain maybe what you want to say.
Good morning. Yeah,
Hi.
I talk about that when you talk about biomineralization, and
Yes.
we study things like that when you talk about fossils. Fossils are not bones. Are bones mineralized by something, by other minerals in the ground. So when you talk about that, I directly think about study structures like fossil cells. We can see protofeathers or fossil cells structures, like know what a dinosaur or a mammal, what is its diet, if he's I don't know how to say carnívoro or herbívoro in English.
Carnivorous.
Yeah.
Yeah.
And you have a lot of information we can do with we know that.
So yeah, that is his question. He wants to know if you can study fossil cells, right?
Yeah, I honestly don't know.
There are studies in biomineralization on fossil cells.
I honestly don't know. I'm not enough of an expert in biomineralization, but I mean, you could certainly email my colleague Phil Cook at ESRF, who would answer that for you. I'm sorry, I wish I knew. I'll have to ask some of my colleagues, because I'm curious myself now.
Okay, so maybe you can just send us an answer to Edgar, and we send it to the student. But yes, we are in Amazon, right? So in the Amazon rainforest, this biomineralization could be of extreme use, because we know there are several species which have never been discovered, and who knows, this can be a useful tool for our region.
Yeah.
Any more questions? Yes, Pushpito, you can ask the question. No. Your microphone, please, Pushpito.
Oh, sorry. Okay, good morning to all of you, and huge. I would like to thank you for a very nice talk. It's really nice, even for a theoretician like me. Yeah, it's very didactic. I just have a basic question, very basic question. Maybe it's just out of curiosity. You told about dark field spectroscopy, X-ray techniques, and you mentioned about bright field X-ray techniques. And in dark field X-ray techniques, you can, as I understand, you can choose a particular, you can select a particular piece of the sample, and you can study it through scattered beam.
Yeah.
But in bright field, isn't it possible? Just to understand the difference between these two.
No, because in bright field, your contrast becomes purely from the absorption of the X-rays. So if you're looking at, for example, a piece of, let's say, a piece of aluminium which is completely dense, then the different grains have no change in density, so it's very difficult to see anything. That's why you don't do tomography on solid aluminium so often. So by using the contrast from the grain directions, that allows you to sort of see something inside the materials.
Okay, that's nice. Thank you. Thank you so much.
You're welcome.
Any other question? So, well, it was a wonderful talk. It was very nice having you with us.
It's very nice to be here.
We had your contact through our ex-student from this university, of Leonardo. And well, he keeps the name of UFA and does a wonderful work with you. And maybe, who knows, one day you can be here with us.
Surely,
I hope to visit someday, yes.
Surely, why not? Yeah.
It will be just beautiful to receive all of you. It has always been offline, but well, during this COVID, we don't have the possibility to do anything maybe offline. So it was the only way we could do. We had postponed 1 year, but still the situation continues. But anyway, thank you. So I would like every one of you to thank Dr. Simons for a wonderful talk. And if possible, open your videos to just take a picture of all of you present. Pushpito, I would request you to just take a picture of all of us and just register this beautiful moment. All of you, if possible. So just give a big hand to Dr. Simons.
Thank you.
Maybe we can wait just 1 minute, maybe.
Yeah, just 1 minute.
Yeah.
Okay, take him. Okay, thank you so much.
Okay,
Thank
Dr. Simons. Okay, thank you. Bye-bye.
Bye.
And well, before just going out, I would like to tell you that our next talk will be from Dr. Joaquim Agostinho Moreira. He will be talking about playing with octahedral distortions of RBO3 perovskites. Ok? Então, próxima palestra vai ser do Dr. Joaquim Agostinho Moreira, e ele vai falar sobre o título que acabei de falar, é Playing with Octahedral Distortions of RBO3 perovskites. So, who are interested are welcome to participate in the next talk. Ok, see you. Vejo. Até a próxima, às 10h30.